All right, now that we know what that definite integral means, let's try a couple of examples where we approximate the area under a graph. Okay, in example 2, let's approximate the integral from 0 to 4 of 2x dx by using 4 rectangles of equal width whose heights are the values of the function at the midpoint of each subinterval. Okay, so in the definition here of our definite integral, it is a limit as n goes to infinity. And so this is going to end up being the exact value. Okay, we're not quite ready to do the exact value. We're going to continue with approximations. Okay, so when you see that word approximate and they're talking about some number of rectangles, then we do need to get a little bit more specific about what point in each subinterval we choose. Okay, so the arbitrary point in any subinterval and getting the exact value of the definite integral, that's this limit process. And like I said, we're not quite ready to put that into use yet until we get to section 7.4. Okay, so for now, when you see this, it will say approximate, and then you see this thing, that just means that we want to find the area underneath the function that's in there on some interval from 0 to 4. On the next one, we see the interval is from 0 to 5 and using so many rectangles. Anyways, what I want to do is set this up with a little bit of a picture, and then we want to find out that delta x value, so the width of each rectangle. And then I'm going to use that summation notation just to make it look a little bit more formal. Okay, but I definitely want to get a picture going. So when you see approximate, that means we're doing this add up the rectangles process. So the function in question here is that 2x. So you want to think about that as like f of x equals 2x. So that's actually just the equation of a line, right? Y equals 2x. It's like y equals mx plus b. So there's no plus b there. So this is just the equation of a line. So I'll get my little XY axis going. And I'm purposefully leaving it like this, where the XY axis is like this, because all of the action for this problem, and it definitely helps to think ahead a little bit, all of the action in this problem from 0 to 4 with the equation is 2x. Some kind of straight line that goes right through the origin, and we know that the equation of it is 2x. And we're going from 0 to 4. Okay. Now we want to use 4 rectangles of equal width. So that means we want to use n equals 4 for our delta x. And then we want to use midpoints of each one. So we got to come back to that a little bit because we are going to have to be more specific about choosing midpoints rather than just any arbitrary point, because the arbitrary point only works when you're doing the limit process or if you're doing an enormous number of rectangles. Okay, so let's calculate that delta x. So delta x, remember it's b minus a over n. Okay, and so in this situation, we're going from 0 to 4. So that's 4 minus 0 over 4. And so we get 1. Okay, so we have widths of 1 each time. And so if we're dividing up this 4, it's going to be, and it's a good idea to get this somewhat accurate as you're dividing this up. And we want to do midpoints of each subinterval. Okay, so looking at the way that I have this graph drawn so far, we're not doing left endpoints or right endpoints. We need to do midpoints. So we need to further divide up all of these little pieces into the midpoints. Okay, and so if I get my drawing going, it looks like the first midpoint is going to be 0.5, and then 1.5, and 2.5, and 3.5 are those midpoint values. And so I want to get a drawing going. So the height of the rectangle would go straight up from 0.5 and touch the graph. And then since the width of each of these is 1, it's going to go across halfway in both directions. So that's like the midpoint. Okay. I go over to the next midpoint, this 1.5, I go up and I see where it would touch the function, and I go halfway in both directions. Like that. Okay, for the 2.5, I would do the same thing. I go up and I find the function, and it should go half in both directions. And it's okay if the drawing's not perfect. Those obviously don't look like the same size, but the point is it's the midpoint process. So same with the 3.5, the 3.5 would hit, and then you go halfway in each direction until we get to the 4. Okay, so we're specifically choosing midpoints. Okay, so let's do the fancy notation here. Area equals the sum, and we want to go from I equals 1, always starting with I equals 1, and we're going to n. And in this case, n is 4. And I'll write it out. It's going to be f of x sub I times delta x. Okay, so that's just the fancy notation. We're obviously not doing a limit. We're just doing 4 different ones. Okay, and each x sub I that we're doing here, it's specifically midpoint values. Okay, it's not arbitrary values. Okay, so let's start with I equals 1. Well, we can actually go ahead and just write this all out now. And like I was saying earlier, we know that that delta x is the same every single time. So you can write that just factored out if you want. It's a 1, so it's not too big of a deal to deal with. But let's go ahead and write this out. F of x sub I, so that's going to be f of the first one, and that had a height with a function value defined at 0.5, so 0.5. And then times delta x, it's times 1 each time. And I think in the very first examples I was doing, I was putting the width in the front times the function value, but the order doesn't matter for the length times width of the multiplication. Okay, plus the function value when I equals 2, so that's going to be in the second interval, and the midpoint that we had to pick from there was 1.5. Okay, times the delta x, which is just the 1 again, plus the midpoint when I equals 3. Okay, so for I equals 3, we're in the third rectangle, so that's the 2.5 function value, times 1 again. And then now we have I equals 4, so this is where we would stop. And then this is the fourth rectangle evaluated at the midpoint, which is 3.5. And then times that same delta x each time. Okay. So I'll write this out again. It's for f of 0.5. Remember that the function we're using is 2x. So it's going to be 2 times 0.5. I don't need the times 1 anymore. Okay, those are all just going to be times 1. And then so this is 2 times 1.5 function values. It's just 2x each time. So 2x, 2x. And then this is certainly not the exact value, or it could be, but this is the answer if we were told to use 4 rectangles with the midpoint process. And this actually might be the exact value because there might be an equal amount of overestimating and underestimating because this is a straight line and we're using midpoints. That's actually kind of a fun question to ask, and I'll come back to that in just a minute. So I'll type this all out, 2 times 0.5 plus 2 times 1.5 plus 2 times 2.5 plus 2 times 3.5. So I got exactly 16. So my question, and I was kind of thinking out loud, is this an underestimate, an overestimate, or is it possible that that's actually exact? Okay, now that's the answer for the way that they wanted us to set up this problem, but I'm curious, is this exact? Because in general, especially if you've got a curving function, it's only exact if you let n go to infinity. So for this one though, notice that because it's a straight line, like that underestimate and overestimate, do you think those might be equal? So the underestimates and overestimates might be canceling themselves out perfectly. What do you think? Well, let's think about this. For this one, we can actually use geometry. For this line that I just drew here, if you want to think about it, we have I'm just drawing like a mini version of it. We have a right triangle here. We know how to find the exact area of a right triangle. So what was the length all the way across the bottom? The length all the way across the bottom was 4. And then if I would continue this 4 to continue all the way up to where it would touch the function up there, it would be 2 times 4, because the function value f of x is 2x. So 2 times 4 is 8. Okay, and then remember that the area of a triangle equals 1/2 base times height. And so this would be 1/2. The base all the way across would be 4. And then the height right there would be 8. So that's 1/2 of 32. Hey, check it out. So kind of interesting there, since this function is a nice straight line and we use the midpoint method, our approximation using 4 rectangles actually gave the exact area because the underestimate, overestimate parts cancel out perfectly. Okay, now kind of interesting. You can use geometry to confirm your answers or to try to think about the answers there. Okay, but if you've got curving functions, then it definitely would not be exact. Okay, but kind of interesting there. Okay, I hope that was amusing at least. Let's try example 3. Approximate the integral from 1 to 5 of 1/2 x squared dx by using 4 rectangles of equal width whose heights are the values at the left endpoint. Okay, definitely got to get a drawing going here, and then keep in mind that the part on the inside of the integral right there, that is the function that we're using. Okay, so we want to think about that. I'll write this down. We're using f of x equals 1/2 x squared. Okay, they said 4 rectangles. Okay, so that means we want to use n equals 4 of equal width, of course, whose heights are the values of the function at the left endpoint of each subinterval. Okay, so we want left endpoint. We should definitely get a drawing going. We're going from 1 to 5, so we want to calculate, let's calculate the delta x right now. So that's b minus a over n. So that's going to be 5 minus 1 over 4. All right, that's convenient. That comes out 1 again. Okay, it's not always going to come out 1. It could come out something kind of weird depending on the number of rectangles and what interval we're looking at. Okay, but that delta x is nice because we can always force it to work to find out what the widths need to be. Okay, let's get a drawing going here. And again, I think everything is happening in the first quadrant, so I'm going to give it some extra space here in the first quadrant. And so 1/2 x squared, that's a parabola that's just kind of wide, kind of flattened out. So I'll draw it kind of, when I'm drawing these, I kind of exaggerate it a little bit just so that I can really draw my rectangles pretty good. Okay, so that hits right there at the origin, and then it's just this parabola opening up like this. And so we want to go from 1 to 5. Okay. And so we want 4 rectangles, and so we want to divide this interval up into 4 different intervals, and they're each going to have a width of 1. So let's see, 1 up until 3 would be halfway. So I just want to get these going like so. Okay, now we don't want midpoints this time, we want left endpoint. So this is where it's a good idea to get a drawing going for left endpoints, and we're starting at the x value of 1. That means I want to go over and grab the function value at the left end, and then make that the left corner and go straight across with the rectangle. Okay, then moving over to the next one, I want to make it left endpoint, so it would be right there, and come straight down and then straight across and over. Okay, another left endpoint would be at the 3, come straight down, and then go right straight over. Okay, and then the last one, left interval, left endpoint is going to be at the 4. So grab the function value at the 4, come straight down onto that rectangle, and then over to the 5. So that would be the drawing that does left endpoints. Okay, let's write down using our fancy interval notation, or that summation notation again. We're still just going from I equals 1 to n, which is 4 again. And it's just going to be f of x sub I times delta x. Okay, and that's just kind of fancy notation there. Now we can pretty much just do this the way that we would have done it in the previous example, or like even all the way back to example number 1. Okay, so f of x sub I, so in the first interval, since we're doing left endpoints, the height of that first rectangle is the function value right there at 1. So it's going to be f of 1 times delta x, which is 1. Okay, now we move over to I equals 2. Okay, and now we've got the function value for the left endpoint for that interval gives us the rectangle that has the height of a function value at 2. So f of 2 times that same delta x. And then we have f of 3 times that delta x plus f of 4 times that delta x. And we stop. There's no other f of 5 because there's not a function value over on that side. So these are the 4 that we're using. Okay? So then each of those is just times 1, so we can kind of just ignore that times 1. If it was something different than a times 1, then you could factor it out, and that would make your calculations a little bit easier. So for this, I'm just going to ignore that times 1 each time, and this is just going to be 1/2 times 1 squared plus the function is 1/2 times 2 squared plus the function 1/2 3 squared plus the function 1/2 4 squared. Since this is curving, this is definitely not going to be an exact value like it was in the previous one. Okay, and just based on how we're doing left endpoints on a region that is fully concave up, right? That's telling me, especially since it's concave up and increasing, which is also something that maybe I didn't quite mention exactly. Notice that since we're doing left endpoints, it's concave up and increasing. We have an underestimate. But if we were doing intervals, if we were doing left endpoints on the other side, notice that it's also concave up, but it's decreasing. That would be an overestimate if we were doing left endpoints over there. So yeah, I just wanted to clarify that it's not just the concavity, it's also whether or not you have increasing or decreasing. So kind of interesting to think about that. Okay, so it's the concavity, but it's also whether or not it's increasing or decreasing. So for this one, since it's concave up and increasing, we do in fact have that the left endpoints are going to be an underestimate. Okay, anyways, lots of, I mean, just so much interesting things to talk about there. I could go on and on. So let's go ahead and calculate this. We're going to have 1/2 times 1 squared plus 1/2 times 2 squared. If I could type it in right. So 1/2 times 1 squared. Okay, and then we've got 1/2 times 3 squared plus 1/2 times 4 squared. And so I got 15. Is that right? 1/2 plus 1/2 times 4 plus 1/2 times 9 plus 1/2 times 16. I got 15 exactly. Okay, so that is the answer for this problem, but that's definitely not going to be the exact area in the region that we're looking for. Okay, that's the answer to this problem using 4 rectangles with left endpoints, but that's definitely an underestimate because there is like missing space. Right, and yeah, very interesting to note. I was mentioning the concavity earlier about how that determines overestimates or underestimates, but it's not just the concavity, it's also whether or not it's the function is increasing or decreasing. Because like I said, if we're looking over there on the other side, we have overestimates for left endpoints. Okay, interesting stuff. So I will make a separate video to talk about the total change. Stick around for that.